Hi everyone, I'm Patrick Taylor. This is an introductory video for a series of videos on the topic of logic in computer science. In this video, I'm going to give you a general overview of logic and give you some motivating examples to show why logic is a useful exercise in computer science. But first of all, as a 10,000-foot view, it's worth noting that when we talk of logic, we're talking about a massive field. We're not simply talking about one individual logic, we're talking about many logics, designed for many different purposes. And the aim of these videos isn't so much to present one individual logic, but to give you a framework with which you can approach a new logic and understand it. Because all logics, to a certain extent, have some similar elements to them. So although we'll be looking in a fairly abstract way at the topic of logic, it's not helpful to look in a purely abstract way. So we'll go through these videos using the long-running example of propositional logic. If you're a computer scientist or a mathematician, maybe a philosopher, you've probably come across propositional logic before, or predicate logic or first-order logic. They're two separate logics, and we're going to be looking at the first. If you've not, don't worry, it's a relatively simple logic and easy to understand. So as a general overview, let's have a look at what logic is. And ultimately, what logic allows us to do is reason about the real world. And we're going to have a look first of all at logic using an intuitive example. Not from computer science, but from everyday life. And we're going to be thinking about this through the context of an engineer designing a building. Now, in the real world, a building is obviously a very complex thing to design and make. It needs to fulfill a whole load of functions. It has to stand up, it has to not fall down, it has to be heated and ventilated correctly, it has to be inhabitable, and whatever else engineers and architects think about when they're designing buildings. And we need a way of being sure that a building we design will actually fulfill all of these functions. And the first thing we'd quite like to do when we're thinking about this is to have a way of writing down stuff about the building. A way of representing the building, not in real life, but on paper. And this brings us to the concept of syntax. Syntax is, on one level, literally the marks we can make on a piece of paper. And from the engineering context, we're very familiar with this idea. An engineer will quite naturally sit down at a bit of paper, or perhaps in the modern day a piece of software, and develop a drawing of a building before it is built. Create a diagram, a schematic. But we need some way of linking what we can write down, the syntax, to the real world. And in a drawing example, we barely even think about this because it's so obvious. A length on a piece of paper is going to correspond to a length in real life. Perhaps 1 centimetre on your paper is 100 centimetres in the real world. And when we do this with logic, this correspondence isn't going to be as clear. So it's very important that we have a clear distinction between these two things, what we write down and their meaning, and to be able to model the real world and not include all elements of the real world using the semantics. A good example of this is how engineering drawings have evolved over time. A modern drawing is going to be very schematic, very diagrammatic. But if you look back 100 years or so, or maybe to Victorian period, the diagrams there were incredibly rich. They included colour and shading and light, and they were modelling a lot more of the real world than we do in engineering drawings today. But it's not quite enough simply to be able to represent the real world using syntax and to know what it means using the semantics. We also want to be able to reason about the real world. We want to be able to make sure that when we have our drawing of our building, that it does fulfill all the functions. It does stand up and it doesn't fall down. And this brings us on to the third and final part of what we're going to look at as logic, the deductive system. And we're very familiar with the sort of deductive systems we use in engineering. So an engineer may well use calculus or algebra or geometry to analyse things that they design. And these three things, semantics, syntax and the deductive system, we call a logic. And each logic will have these three elements. They may be more or less obvious and you may need to dig a bit deeply to see what each of these are, but this is the framework that we're going to be examining over the next 3 videos. So now I thought I'd give some motivating examples. Some examples to show you why studying logic is a useful exercise. And the first one, if you are from a computer science background, is probably very familiar to you already. Certainly if you've used any statically typed programming language, C++ or Haskell perhaps. Type systems. So when you write a computer program, before compilation in statically typed languages, the compiler will go through your program and check that all your usages of types and functions are consistent. Super simple example that you're not, for example, passing an integer into a function which expects a floating point number as an argument. If the programmer is in error, the compiler will throw up an error and stop compilation until this problem is fixed. But it's very important for those who are designing the compilers to know that their type checking and their type inference algorithms are correct. That they will flag up errors when the programmer is wrong, but they will allow compilation to proceed when the programmer has got it right. It also doesn't help that modern programming languages can be huge and incredibly complex. And it's pretty much impossible for a human to eyeball a type-out, type-checking algorithm and see whether it is correct. We need some help with this. We need logics to analyse our type systems. And this gives rise to the whole field of type theory. The second example I'd like to give is from the field of hardware verification. So way back in 1994, Intel released a chip, and it was a chip which had a problem with it. This gave rise to what is now a relatively well-known bug called the FDiv bug, standing for floating point division. In certain circumstances, fairly edge case circumstances admittedly, the floating point algorithm in this chip released by Intel produced incorrect results. And it's important to note here that incorrect results and incorrect algorithms, incorrect design in hardware is a lot harder to fix than it is in software. In software you can simply, most of the time, push an update to the user. In hardware, in silicon, you have to design a new chip, you have to manufacture that new chip as well. And that's very expensive. So it's very important in the hardware industry to get designs right first time. This is difficult. Bugs appear all the time in software and it's no different in hardware. And this has led to a certain push in industry to utilise a technique called formal verification. So at a high level, in formal verification, we write a specification for what we want something to do, in this case a piece of hardware, and we write an implementation for that piece of hardware. And it's possible, through logics, to be able to mathematically prove beyond doubt that an implementation, which is an incredibly complex piece of code, matches a specification, which is far easier to understand by humans and make sure it's correct. So in this video, we've taken a look at logics at a high level. We've looked at an overview of logic and some motivating examples. In the next few videos, we're going to be taking a look at each of these three constituent parts of any logic individually, focusing on propositional logic as an example. And as a final note, it'll be useful in the next few videos to have a bit of computer science background knowledge, but don't worry too much if you haven't. All it'll mean really is that some of the examples may be slightly less meaningful. So in the next video, we're going to start by taking a look at semantics.